All right, let's say we're trying to find the momentum of an object that's sliding across the ground. So let me do this. Oh, I'm going to have troubles today. Let's see here. Here's our box. Let's just say it has a mass of m, and it is moving along with a velocity of v. If it was moving to the right, we would say that the velocity is p. The momentum is equal to, let me get this out of here, the mass times the velocity. So let's say it has a mass of 10 kilograms and a velocity of 5 meters per second. All you would do is multiply those together. You put in your mass, 10 kilograms, your velocity, 5 meters per second, and that would give you a momentum of 50 kilograms meters per second, or 50 Newton seconds. If it was going in the opposite direction, let's just say instead of it traveling with a positive 5, it was going in the negative direction. Here we go, pen tool is working. Let's say it was going this way with a velocity of negative 5. And the mass again was 10 kilograms. This would be simply same formula, but since it's a vector, 5 goes in negative, and it's not going to be squared like energy. So the direction makes a difference. The mass is going to be 10 kilograms, and your velocity is going to be negative 5 meters per second. So you'll get a momentum of negative 50 kilogram meters per second, or negative 50 Newton seconds. Okay, fair enough. But what about an object that is rotating? Well, that's a little bit different. So same idea. The formula we used before was P is equal to m, the mass times the velocity. But now we're going to come in and say L, angular momentum. This is angular momentum is equal to I omega. So we're going to replace the mass with the moment of inertia and translational velocity with angular velocity omega. All right, so let's take a look and see what that means. Well, there's two different ways to do that. Let's say that we have, I would love to have a disk on my, dang, what's going on here? There we go. All right. So here is our disk, and let's say that it is rotating. Get that dot out. Let's say it's rotating in this direction here, going around this way. This is negative, right, when it spins this direction. So let's take a look. Let's just say for funsies, it has an angular velocity equal to 100 radians per second. And at this point, you should be able to convert from RPMs to radians per second. We'll get into that in a second. Well, let's see here. Let's say this has, we got another radius. In this scenario, the radius, let's just say it's 0.5 meters. I'm just making this up. And then we'll say the mass of this thing is always 10 kilograms. And it is important to note that this is a disk. Why is that important? Because that tells us what formula we're going to use for the moment of inertia. So let me make sure I put this in here as negative because it's rotating in this negative direction. Remember, clockwise is negative, counterclockwise is positive. And so let's calculate the moment of the angular momentum. So L is going to be equal to the moment of inertia times angular velocity. The moment of inertia for a disk is 1/2 mr squared times omega, and that's going to give us a angular momentum of 1/2 10 kilograms times 0.5 meters. Make sure you square it times the angular velocity, 100 radians per second. And remember that radians is a ratio, so technically doesn't have a unit per se. We just call it radians. And so if we put that in a calculator, okay, let me get this out of the way because I realized I made a mistake right here. If you put that in your calculator, you will get 125 kilogram meter squared per second squared, except I was not paying attention, and this, kids, should be negative. So you should have a negative answer. So if an object is spinning in this direction, it will have a negative angular momentum. All right, if it was spinning in the opposite direction, that would be a positive 100 radians per second, and then you would get a positive answer. Remember, if you're given RPMs, the way we take care of that in class, we divide that by 60, and then we multiply everything times 2 pi. If you need to see that in dimensional analysis, let's just say we had 25 RPMs. Say 25 revolutions per minute. I always do things this way. I know you guys get mad, but that's how I like to do it. If I don't see my units cancel out, I feel the fabric of the universe is going to unravel. And so if I put that into a calculator, .62 radians per second. The setup's correct. I don't know if the math is correct. Make sure you check it. All right. What about an object that's spinning like this tether ball? Love tether ball. All right. So let's say we have this object going in. Let's spin this one in the positive direction. Oh, this isn't really going to fit. Move it down a little bit. Okay. So let's say, let's make this a little smaller. Say this is the axis of rotation right here. It's nothing if I can't make that. All right, here's the axis of rotation, and our tether ball is going to be spinning in this direction. Yeah. Well, there's this really interesting thing that happens here. We know from our formula that for the angular momentum of an object that's rotating in the center, is L is equal to I omega. But in this case, that's not really going to work for us. And so we could take this object here and say, well, what do we know? Well, we know that I jumped ahead of myself really quickly. So we know that, and I don't know if I'm looking at this correctly or not. This is just how I see it in my mind. I know that as this object is spinning around in a circle, there is that instantaneous tangential velocity. Sorry, my writing tools, and it's going to be tangent to this circular path. And at this moment, it's going to have a momentum of P, which is translational. It's going to be mv. And if I wanted to find the angular momentum at this edge here of an object that is spinning in a circle, and I know the velocity that it is traveling, I could take the radius here and multiply it times that, and that will give me the angular velocity. So that's going to be rp, which is going to be r times mv. And you're really going to see this usually as mvr. And this is how you find the angular momentum of an object that is being spun in a circle, like a tetherball, if you know the mass of the object and what have you. So that formula becomes L is equal to M or V or MVR, however you like to look at it, doesn't make a difference. So let's take a look. Let's say we have this object that is being spun in a circle. It is traveling 10 meters per second. I'm just making this up here. 10 meters per second. It has a mass of 0.25 kilograms. And let's find the angular momentum. What else? I need a radius of the circle. Let's just say it's 0.5 meters for funsies. Let's put it all in. It's spinning in the positive direction. So we would look at this and say, oh, look at that. LAUSD. All right, let's see here. The mass is 0.25 kilograms. The radius is 0.5 meters, and the velocity that is traveling is 10 meters per second. You need to be in meters per second. And so when you multiply this out, let me put this in a calculator. You get 0.25. $125 kilogram positive meters squared per second. Look familiar? Very fun. Okay, now here's something that we need to know about this. It's going to come back to us later because an object that is traveling in a straight line then technically has angular momentum, and that's going to be important when we get into our FRQs. So make sure we remember this. All right, that should tell you everything you need to know.